Hello, welcome back, guys. We are going to be going over Chapter 11, Transformations, Symmetries, and Tilings today. So let's go ahead and get started. All right, we are going to start with rigid motion. And what the question asks is we have this line of symmetry right here. And they're wanting to know what this figure would look like if it's reflected over the line. Now, somebody else has done this, and what they did is they started with this point right here, and they turned it 180 degrees to where it would follow this arch right here. Now, when we look at this, this is a rigid motion of 180 degree rotation, but it's not exactly a reflection of this figure over this line of symmetry right here. So we are going to come back to just this regular shape, and we are going to put our line of symmetry in. And now when you think reflection, I'm thinking when I wake up in the morning, I look in my bathroom mirror, what's coming back out at me? Or if I was to hold a piece of paper up to a mirror, what would it look like on the other side? So if we were to reflect the figure, this is what it would look like on top of it. We see that it's reflecting. This point reflects over to here. This point reflects over to here. And we see that these points are reflecting because there's no spot right here, so it's reflecting over. And so this is what the figure would look like towards the end. Now we are going to move on to lines of symmetry. We have this figure right here, and what a line of symmetry is if I cut a shape completely in half directly down the center, would it be exactly the same on both sides? If I were to just fold it completely in half, would one side look the same as the other? So on this figure right here, we have a line of symmetry right here and a line of symmetry right here where we cut it in half. And if we were to fold it over, these sides wouldn't match up because this side doesn't have a side over here. So this does not have any lines of symmetry. Now we have this diamond shape. And if we would cut the diamond right here across the center and right here down the center, folding them in half on each line, it would cut directly in half. So that is a figure of line of symmetry. Now this shape right here is just almost the same as this shape over here. So we already know from this shape that it does not have any lines of symmetry. Oh, I do not know why they're popping up over there. I apologize, guys. So now we have a triangle. And this triangle, if we were to cut it down the center here, down the center here, and down the center here, they would all fold over and be exactly the same on each side. So that is a line of symmetry. Now we have this 3/4 circle, not quite a circle, not quite half a circle. If we were to cut it in half this way, when we fold it in half, it would be the same, but we could not cut it this way. So we only have one line of symmetry here. Now we have this rectangle. Again, I apologize about these two lines. They're getting in the way. We have a rectangle that if we cut it directly down the center horizontally and directly down the center vertically, they would both be lines of symmetry. So it would, I apologize, guys, about these animals. They are going crazy. They would be two lines of symmetry, one going horizontally and one going vertically. So now we have another triangle, and just like this one before, we are going to do a line of symmetry this way, and we see that it only has one line of symmetry. If we were to cut it this way, this isn't a perfect equilateral triangle, so it will not fold directly in half equally this way or this way either. Now we have a hexagon. Now a hexagon, it will fold equally this way, on this line, Oh, I apologize. And on this line, so we have 3 lines of symmetry because we can fold a hexagon in 3 different halves and they would all be equal. Now we are moving on to 180-degree rotation. Now, 180-degree rotation, if I were to grab a figure at any given point and move it 180 degrees, would it look the same as it did from the beginning? So here, we are going to take this point, we're going to just say we grabbed it by this point and moved it 180 degrees. This is what it would look like afterwards. So we know that this figure has a 180-degree rotation. Now we're going to do the same with the diamond. We're going to grab it by this top point, move it 180 degrees, just following this line right here. And it would also have a 180-degree rotation. We're going to do the same with this figure. And again, like we did with the lines of symmetry, this figure is very similar to this one. So if we grabbed it by this point and moved it 180 degrees, it would come out looking the exact same. Now we're going to move on to our triangle. We're going to grab this triangle by this point and we're going to flip it 180 degrees. And just from what we know from triangles, we know that it's probably not going to look the same because it only has 3 points. And so when we turn it, it does not have a 180-degree rotation. Now we're going to do the same with this 3/4 circle. And at the end, it will not have a 180-degree either. And now with the triangle, or I apologize, a rectangle, we're going to grab it by the middle point. You can grab it by any point. You can grab it here, flip it 180 degrees, and it will come out the same. We have another triangle over here, and we flip it. It's going to be pointing the opposite direction, so it will not have a 180-degree rotation. Now we're going to move on to our hexagon. And when we flipped that one 180 degrees, it comes out looking exactly the same. So it does have a 180-degree rotation as well. Now we're moving on to tiling. Now, what is tiling? So what we're going to do is we're going to start with these triangles right over here. I have one equilateral triangle. And what tiling is the same shape repeated over and over again, laid next to another shape. And you can see this triangle is just flipped over, facing this way, facing this way. And what makes it true tiling is these shapes, they cannot overlap and they cannot have gaps. Now we see down here in this shape with this octagon. Yes, I apologize, our octagon. When you lay them side by side and have each spot touching, it creates other shapes where we can fit squares into here. And it, unlike this triangle, it's still considered tiling because we don't have to use the same one shape. It's just a repetitive pattern of shapes that are used over and over again without overlapping or any gaps being given. So now we are going to move on to this vertex figure. A student was asked to create a vertex figure, and she thinks she came up with one. It doesn't overlap and it doesn't leave gaps. Now, to make it a true vertex figure, we have to be able to tile it and repeat the shapes over and over without overlapping or any gaps given. So we're going to go ahead and put our hexagons in place. And then we're going to start putting the pentagons every other space. And we can already see right here it leaves gaps. And then over here it overlaps. So this is not a true vertex figure. Now we're moving on to congruent triangles. And we're wanting to know, how do we know these triangles are congruent? We have triangle PQT and triangle PST. And we want to know if these two triangles shaded in right here and right here are congruent. Now, we see that they share a line already, PT, so we know that one side is already going to be equal to the same side on the other triangle because they share this line. Now we move on to line segment PQ and line PS. And we can see that there's a dash mark on each line. That indicates that these lines are congruent. And the same with line QT and TS. They have two dash marks indicating that that line is congruent as well. So this is what we would call the SSS congruent triangle. It's side, 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 stating that all three sides are the same length, making the triangle similar. If all sides to the triangle are the same, then the triangles are congruent. Now they want to know, is triangle QPT and SPT are the congruent? And yes, that is what we just figured out, is that all three sides are congruent. So it's side, 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 congruent triangle. Now we want to know, is angle QPT the same as SPT? Now what we know before is that these sides are already the same length. This side, line PT and PQ and PS are the same length. So we already know that the angles are going to be the same as well. Because if the lines are the same, the angles are going to be the same. So those angles are congruent. Now we want to know if angle QPV, or triangle QPV and triangle SPV, this triangle right here, are congruent. And we know that these two lines, lines PQ and PS, are congruent. And we know that line PV is congruent because it's a line that is shared. And we also know that angles QPV and SPV are the same because they're the same angle from the bigger triangles. And that would be a side angle side congruent triangle, which means that the triangles are congruent because the side angle and side are congruent. As long as two sides and an angle are congruent, the triangle is congruent. Now what we want to know is angle QVP if angle QVP is a right angle. Now what we have here is a horizontal line that goes straight across and a vertical line that goes straight down at 180-degree angles. Now what we know is a line is 180 degrees, and when you have one that comes perfectly perpendicular, it will always be 90 degrees. So we know that this angle is 90 degrees. Now we have a circle with a pentagon, with a triangle, and a whole bunch of lines. And what we are wanting to know is the angles of these. So we are going to start with the circle and the triangle, the pentagon, I apologize. And if I were to put a center point right here and connect every single point that touches the circle to this center point, we would have 5 different points that touch the outside of the circle that can be drawn to the inside of the circle. So we know that the area, are all angles on a pentagon added together, are 360 degrees, and we would divide that by 5. So each angle is 70 degrees. Now we are going to do the same for the triangle, and we know that a triangle also is 360 degrees equally with all angles added together. So we know we're going to do the same. We're going to put a center point in and connect all the points that are touching the circle to the center point in the circle. And we'd get 360 divided by 3, which is 120. And now we are going to subtract the angles. We're going to subtract 120 or 72 from 120. We're going to get 48 degrees. Now, 48 degrees is not our answer because what we're wanting to know is the angle of NOP. Oh, it did not pop up the label right here. I apologize. angle NOQ is what we want to know the angle of. So 48 degrees is for the entire figure, and we're wanting to know just NOQ. So we are going to draw a line of symmetry right here and cut it in half. And so 48 divided by 2 is 24. So we know, oh, I apologize. So we know NOQ is 24 degrees. Now we have the height of a cliff. Look at this. This girl over here, we'll call her Sally. Sally wants to know how tall this cliff is. And she's holding up a ruler to try and figure it out. So we are given some information, and let's see. What we know so far is the distance. Let me go ahead and move my thing over so that I'm not blocking anything. The distance from Sally's eyes to the ruler is 2 feet. We also know that the ruler markings differentiate by 1.5 inches. And the cliff is a 1/4 mile away from where Sally is standing. And we are given that 1 mile equals 520 or 5,280 feet. So where do we begin? So we need to figure out the height of the cliff, and we see that we have some triangles in this equation. So we can use those to help us figure this out. So what we're going to do is we're going to do the distance between the ruler markings divided by the distance from eyes to the ruler, which is also equal to the height of the cliff divided by the distance of the cliff. So we are going to take those numbers that were given to us and go ahead and plug them in. So we have 1.5 inches divided by 2 feet, which is equal to the height of the cliff divided by 1/4 mile. Now we don't have the height of the cliff. That's what we are wanting to figure out. So we know that 1/4 mile is our distance from Sally to the cliff, but we're wanting to know it in feet. And 1 mile is 528 feet. So we're going to convert our miles to feet, and we'll get 1.5 inches divided by 2 feet, the height of the cliff divided by 1,320 feet. And we're going to cross multiply. So we're going to multiply 1.5 times 1,320 and divide it all by 2 to get the height of the cliff. Now we are asked to round, so we are going to get approximately 82 feet is what the height of the cliff is for this figure. All right, and that is all I have today. Thank you guys so much for watching, and I look forward to seeing you guys again.